Hello, everyone. Good morning, good afternoon, and good evening. My name is Alireza Jofai, and I'm chairing the Cybersecurity and Privacy Technical Committee of the IEEE Consumer Technology Society. As on behalf of the IEEE CTSoc Society, we are very pleased to invite you to join us for the second webinar of the technical talk series that the Society has organized for you to get to know the recent findings and research happening in the field of the consumer technology. For today, we have two talks. We invited two distinguished guest speakers from Australian Defense Cybersecurity Lab, and as well as a professor from Science and Technology Research Lab in Japan to deliver two technical talks for you. Before we start the technical talks, I would like to invite you to listen to a welcoming message from the Vice President of Technical Activities of IEEE CTSoc Society. Unfortunately, Fabrizio couldn't make it today. He's flying overseas. We wish him safe travels. But he sent us a video which we would like to share with you to learn more about the activities that society has organized for its members. So now I'm sharing the video from Fabrizio Lamberti about the technical activities of the society.
Hi, everyone. Good morning, good afternoon, good night, depending on where you are connecting from. My name is Fabrizio Lamberti. I'm the Vice President of Technical Activities of IEEE Consumer Technology Society, and it is my pleasure this series of talks originated within the context of the technical activities area. This area of the society is responsible for managing and covering the technical aspects in the field of interest of IEEE Consumer Technology Society. And there's a website dedicated to this area. And the activities are promoted through mainly the technical committees and the future directions committee. I think that many of you are already aware, are members of the technical committees. There are 15 technical committees which have been established starting January 2021. As you can see from the names, they cover the areas, all the areas of interest of the society. The technical activities area is organized in these technical committees, which are reporting to the technical committees board, and the board is reporting to the VP of technical activities, and also the future directions committee is reporting to the VP of technical activities. As you can see, the board is a supervisory body in which are represented the CTSoc president, the VP of conferences, the VP of publication, the VP of industry and standard activities. So basically, you see that the technical activities are covering all the areas of the society. And within the board are represented the officers of the 15 technical committees. Each technical committee has a chair, as a vice chair, and as a secretary. Each technical committee has a website in which basically there is a description of the mission, the objectives. There are the officers and members with their names, with their affiliations, their countries. Here you have the officers of the 15 technical committees. The officers are elected. These are the names for the second term, 2022-2023. As you can see, there are a number of names which are in gray. These are the names which are new from this election. So it's easy to see that there is a change in the volunteers serving the society, meaning that there are experts which are still contributing to the society, and newcomers which bring new blood to the society and its technical committees. As members of the technical committees, you probably joined them if you are members, you probably joined when the committees were established or in a continuous process of enlargement of this family of members. There's a membership application form, which is received by the TC officer, which periodically evaluates the new application and notify the applicants about the outcome of the evaluation. You don't need to be a member of CTSoc or IEEE to be members of the technical committees. So if you are not a member and you joined it today because you got information about this webinar from your colleagues, please consider joining. I will show you the link for to the application form at the end of this presentation. We are now approximately 850, 900 members. Some of them were invited at the beginning based on the service they provided to CTSoc conferences. Some other joined later because we advertise and spread the word also not just to authors of conference paper, of colleagues who served in conferences, but also to authors of journal papers in our publications. And we also reached the network of contacts of our officers and members and through the channels of CTSoc. As you can see, all the committees are well participated. The role of the technical committees, as many of you know already, is to support CTSoc activities in all the areas: conferences, publications, standards, education, and history. Their goal is to investigate, evaluate, and promulgate and foster current and emerging technologies and applications of interest to CTSoc. The goal is to create additional technical committees for technologies of interest to CTSoc and conduct periodic and special technical meetings. New committees can be created in collaborations with other CTSoc technical committees, with other technical committees of IEEE societies and council and other IEEE organizational units, and also define new areas of technology focus and encourage the formation of new initiatives through CTSoc FDC. Just to make an example, regarding conferences, the technical committees are responsible for reviewing and approving the call for papers of conferences, to support conferences by contributing papers and providing reviewers, provide publicity for paper submission and participation in conferences, collect nominations among technical committee members and recommend individuals for serving in technical positions of CTSoc conferences as TPC chairs, workshop chairs, tutorial chairs, publication chairs, and TPC members. They are responsible for providing conference tracks and session chairs and collect proposals for hosting conferences, as well as for academic and industry conference speakers. So basically, they are providing a number of opportunities for members to serve. There's a page devoted to listing outcomes and opportunities of achieved or provided by technical committees. But just to provide you some examples, in the last years, the technical committees have identified technical positions and named service and technical positions for CTSoc conferences like ICC Las Vegas, ICC Berlin, and Games, Entertainment, and Media Conference. They recommended names serving now as associate editors in our publications like the Transactions on Consumer Electronics and Consumer Electronic Magazine. They organized special sessions in journals. They organized workshops and special sessions in conferences. They have been involved in initiatives like the IEEE Digital Privacy Initiative, or they are being involved in initiatives like digital reality and its transformation from the initiative to a technical community. They supported collaboration with other societies like the Signal Processing Society or the Audio Engineering Society. They created special interest groups like the one on the metaverse. And last but not least, they were involved in the organization of several webinars and technical talks. And this is what I'm presenting you today, the technical talks of CTSoc. We build on the success of a series of talks which were organized over the last years in individual technical committees, and we created a brand new series of webinars named the Technical Talks of CTSoc. Basically, every month, 2 technical committees join and organize a talk like the today one, in which they call for volunteers, for speakers among the members willing to give us a talk. And today there will be 2 speakers selected among the members of the SMC and the CEA technical committees. And I want to thank the officers and the chairs of these 2 technical committees, Iman Shutafilal and Bernard Fong, for having organized this webinar. If you're interested in contributing as a speaker, please contact the officers of the technical committees in charge of the month event. The next one will be in July. The SEA and the SPC technical committees will be involved in the organization, but as you can see, the schedule for the next month is already here. You have a calendar. We're still just missing the dates that will be arranged with the speakers. So once again, welcome to this first event of the Technical Talks of CTSoc series. If you are interested in these activities, if you're not a member and you want to join, please frame this QR code and you'll be directed to the webpage of the technical activities area. Thanks again, and I leave the floor to the organizer for the introduction of the speakers and the talks. Enjoy the talks.
Okay, thank you, Fabrizio, for great introduction to CTSoc Society. Now I would like to introduce for our first guest speaker, Dr. Ali Mehrabi from the International Center of Neuromorphic Systems at Western Sydney University in the New South Wales in the eastern side of Australia. The title of Dr. Mehrabi's talk is on intrusion detection on autonomous systems using human brain inspired spiral neural networks. Thank you, Dr. Mehrabi. We are all here, and now we hand on the presentation to you so you can inform us of interesting research area that you're exploring with the Defense Center at Western Sydney University. Thank you.
Great. Yeah, thank you very much, Alireza, for your introduction. Thank you very much for having me here to share with you one of my research topics that I've been working since last 2 years, which is intrusion detection using spiking neural networks. Basically, my presentation is in 2 sections. At first, I will talk about spiking neural networks, why we are using them, why they are important, and what is the difference between the spiking neural networks and the artificial neural networks. And at the second part, I'll talk about the methodology that we use to apply spiking neural networks for security, for cybersecurity and detection of intrusions on the autonomous systems. Specifically, we are targeting GPS spoofing on drones, which is a hot topic in recent years. So, as you know, artificial neural networks are an abstract model of biological neural system. There are several synapses for each neuron, and then the synapses have weighted inputs, and then the weighted inputs are added up together, and they pass through an activation function. And in this model, we are using floating point number systems to do our calculations. Inputs are multiplied by the weights, and weights are and weighted inputs are added together. This is not the way actually a biological neuron do to convey the information from the sensory system to the brain for processing. However, this model actually is very capable to solve many nonlinear problems. Besides, it is considered a very computational heavy and resource heavy and energy craving system. So this energy consumption, this heavy energy consumption has raised concerns between scientists that the power consumption of those systems and the increasing application of those systems will be a concern in near future. And the energy consumption could have adverse effects on our environment. So we are constantly looking for a substitute model, a better way to do our computation in low power and without those complexities. The other thing is that training a neural network could be much more energy consuming that causes the concerns of the scientists. However, training a neural network is very straightforward. We actually select a number of a percentage of our data set. We fit in the selected data set to the network, and we look at the output, and we compare the output of the network with the desired data. We calculate the error using a optimization function, which is usually a gradient descent function. And then we try to minimize error in an iterative process. This algorithm is actually very well known and fixed for training all kinds of neural networks. So if we have a neural network, we can formalize the algorithm and use the same methodology for training the neural network. On the other hand, we have spiking neural networks that are very close to the biological neural systems. In spiking neural networks, like the biological neuron, we have our inputs are in the form of spikes. And like a biological neuron, if those input spikes can rise the membrane potential of the neuron to a level that is called the threshold. If the membrane potential can cross the threshold value, then the neuron can fire, which is considered a spike at the output of the neuron. So those spikes are in the spiking neural networks are modeled as a single pulse, a 1-bit pulse that is as narrow as possible. And this spike is modeled mathematically by Dirac delta function, which is happening at time t. So delta t is the Dirac delta function that is happening at the time t is modeled as the for the spikes. So here you see that the number of spikes are injected to a synapse, and the synapse raises its voltage to the weighted voltage W1, W2, and so on. And those are added up together to raise the membrane potential of the neuron to a high value. If this value reaches the threshold, we would have an spike at the output. As you may have guessed, the training of those spiking neural networks is not as straightforward as it has been on their counterparts, artificial neural networks. And this is because we have 1 bit output and 1 bit input. And as you know, the Dirac delta function has no derivative to be measured, and we cannot measure the error at the output and compare it with the desired value. So mathematically and in reality, we cannot train the spiking neural networks in the way that we do for the artificial neural networks. However, since the data is just 1 bit, and it is considered a new type of data in the space of and in the space and in the time, it's called spatiotemporal data. And so these systems, these spiking neural networks, are very power efficient and very low power systems that they have output only if the membrane potential can cross the threshold. Otherwise, there would be most of the time, a spiking neural network is at its rest time, which has no outputs. So there are both low power consumption. The computation is not heavy inside a spiking neural network, and they are hardware friendly, so they can be easily implemented in the hardware, and we can have many of those hardware neurons in one FPGA, for example. So, as I said, there are some specific rules for implementing a spiking neural network. One of those rules is, as mentioned before, is that inputs and outputs are in the form of spikes. And the other important rule is that a neuron can fire a spike only and only if there has been an input spike at recent times at its synapses. And the other rule, the most important one, is that only one neuron in a layer can fire a spike. This rule is also known as winner-take-all rule, and it means that the winner neuron is the neuron with the highest value and highest priority. So here, at the left-hand side, you see a two-layered spiking neural network. And here you see a structure of a neuron. A neuron consists of several synapses, which is the number of synapses are configurable. And then the output of each synapse is connected to the nucleus of the neuron, where the outputs are added together and compared with the threshold. And if they cross the threshold, they can have an output. However, this output is connected to another comparator, which compares the values of each neuron in a layer of, and the neuron with the highest value and the neuron with the highest priority will be the winner. So at the output of each layer, we only have one spike, and one neuron can fire that spike. as I mentioned, we don't have any classic way to train spiking neural networks. A number of research has been done and still continuing to be conducted on spiking neural networks and training algorithms. At ICNS, we have also created our own algorithm for training a spiking neural network, which is unique in some aspects. And the uniqueness of this algorithm is that we can implement it in hardware. So the consequence of that is that we can have a hardware that trains itself. And this training algorithm is very efficient because as you can see here, each spiking neural network layer can have its own training module. And the training modules are almost independent to each other for each layer. And we use 3 1-bit signals to as a guiding signals to do this training for each layer. Those guiding signals are global attention. We call them global attention signals, which indicates that a label is available for the neuron for the spikes, and we have local attention signal or LAS, which indicates that the next layer has created a spike, and the is-winner signal that indicates that the current layer has created a spike at its output. So as you see here, we are using a reward and punishment method to train our layers. So at the presence of a gas signal, or gas signals tells us that a label is present for the set of input spikes. So if a gas signal is available, we look at the neurons that are fired, and then the neuron which is responsible for firing a spike will be rewarded, and other neurons will be punished. So we do this process for all the layers. And to be detailed, here there is a layer, there is a spiking neural network layer and its corresponding training module. As you can see, the last signal is the OR of all output spikes of the next layer, the gas signal, the OR of the all label spikes, and is event or is winner is event is the OR of all input events, and is winner is the OR of all is winners. So all of them are just 1-bit data. So we look at the input. If there is a activity in the input and there is a winner at the output of the layer, then we'll look at the guiding signal, the global guiding signal. Then we expect to have a label. If there is a label, then we reward the winner. Otherwise, we do nothing. And if there is no winner and gas is active, we punish all neurons, because the neurons are expected to fire, but they didn't. So using this spiking neural networks that we design, and it could be supervised or unsupervised, we design a system to detect GPS spoofing on the drone. So I skipped this to detail how what is GPS spoofing and how it works. But our research is somehow different from the other research, and the difference is that the researches that has been done in the literature are mainly looking at the received data from GPS, and they try to find out if it is a legit data or it is a spoofed data. However, we do the edge computing on the drone. So we have a very small FPGA board attached to the drone, and this FPGA board, which our SNN is implemented on it, is without any supervision, detects that if the GPS signal is spoofed or not. So the drone itself is just receiving the GPS signal and has no idea if this GPS signal is the legit GPS signal or it is manipulated by the adversary. So we need to use a method to find out if the GPS signal is spoofed or not. And this is by looking at the behavior of the drone. So one useful sensor that is used in this research is the accelerometer of the drone. And we just look at two directions and two coordinates of the accelerometer. Accelerometers can be in 3D. They have three components for each coordination, but we just use two coordinates to monitor the signal of the accelerometer. And the method is that the output of each coordinate is between -20 to 20 millivolts. And we map this data, this continuous signal of the accelerometer to 42 spikes. So we actually design a neuron with 42 synapses, and our spiking neural network is just 4 neurons in one layer. So using only one layer spiking neural network with only 4 neurons, we can distinguish if there is any change in the behavior of the drone caused by GPS spoofing. And the results show that if we measure the moving average of the number of output signals, output spikes of the spiking neural network, we can easily find out if there is a GPS spoofing or not. So here you see that if there is no GPS spoofing, the moving average of the spiking neural network is at the higher rate, and depends on how deep is the spoofing, the moving average of the signal will be lower. And then this is the real data of the real data from the output of the spiking neural network. And as we can verify that here, which the moving average is at a higher level, there is no spoofing, and when the spoofing is at its highest level, the moving average will drop considerably. This is actually the my presentation. Thank you very much for your attention, and if you have any questions, I will be available to answer.
Yeah, thank you very much, Dr. Mehrabi, for your very interesting presentation. Do we have any questions from the audience? Maybe you can raise your hand if there is any questions, so we can ask from Dr. Mehrabi. Okay, I've got a question myself. So I just noticed the way that you try to recognize GPS spoofing was through an observation of how the spiking neural network would perform with respect to the changes of the drone. So I mean, in terms of the movement that drones make, did you compare your results with a situation where there is no spoofing, but imagine there is a change in the environment, like, you know, there is too much heat that could impact the you know, the drone movement, or there is a very harsh environment that, you know, the environment very cold, or it's rainy day, it's snowy, or it could be wind. Did you compare your results?
Yes,
Or it's
we have
irrelevant?
compared, yeah, sorry. Yes, of course, we have compared this with a windy situation that will affect the output signal of the accelerometers. So a windy situation will cause the accelerometer to produce more signals, more fluctuating signals. And the good thing of the system is, as I mentioned, is it is an unsupervised system. So an unsupervised system can train itself by the unspoofed data. So when the drone starts its flight, we expect that it starts to train itself. And so in the same situation, it trains itself with no spoof data. And then at the same situation, if there isn't a spoof data, it can actually classify that spoof data as a wrong signal. The other thing is that the system can be very flexible, so it could be commanded to start a new training. So if the situation changes, we can easily command the system to retrain itself.
Yeah, thank you very much, Dr. Mehrabi. Oh, Hiroshi, I have a question, right?
Can I have any question?
Yeah.
I'm sorry, I'm not familiar with these technologies, but for an example of the using application for the drone, what is the inputs of the system? Would you please explain again about
Yes.
inputs?
Yeah, so drones usually have, let me share my screen again. So drones usually have an accelerometer sensor, and this accelerometer sensor actually measures the rapid change in velocity or acceleration in 3 dimensions, X and Y and Z. So as shown here, the pitch, roll, and yaw. So if there is any change in the direction direction in the space the accelerometer will show. We use only two dimensions, X and Y dimensions of the accelerometer. So there are only two signals. So we use these two signals and by the accuracy of 1 millivolt. So each millivolt is considered to be a spike. So, and the acceleration changes from -20 to 20 millivolts. So we have 40 millivolts or 40 spikes. And then we have crossing from minus to 0 and crossing from positive to 0, from plus to 0, which are two different zeros. So we have 42 different signals, and then we inject these 42 signals to a spiking neural network to find a subtle change in the behavior of the drone. Am I answered your question correctly?
Okay, thank you. So the input must be not the direct signal, but the relative signal to indicate the change of the situation. Is it right?
Sorry, would you please say it again?
For example, that input signal is the meaning is the change of the situation. So not the strict information, but the relative information that is changes occurred or not. Is that?
Yes, actually, it is not directly measuring the GPS spoofing, but it measures if there is a change in behavior of the drone caused by GPS spoofing. So if there is a GPS spoofing, the drone has to actually change its direction to go where the GPS signal is directing it. So if there is a change and it is not normal, which can be detected by this spiking neural network, then we consider this as a GPS spoofing.
Okay, thank you.
Thank you.
Thank you very much, Dr. Mehrabi, for your presentation. And now I hand on the session to Dr. Hiroshi Lili, the chair of ACA Society. We will listen to the guest speaker from his technical committee. Thank you, Dr. Hiroshi. I hand on the session to you now.
Okay, thank you. Now change to the ACA group. And I will introduce Mr. Kohei Tomioka. He's a research engineer in NHK Science and Technology Research Laboratory. Let me introduce him. Mr. Kohei Tomioka received BE and ME degrees in engineering science from Kyoto University, Kyoto, Japan, in 2011 and 2013, respectively. He joined NHK in 2013, and since 2016, he has been involved in research and development of image sensors and broadcast cameras, especially for 8K ultra-high resolution and high-speed cameras. Recently, his research interest is on the scene adaptive imaging technology, which is a next-generation imaging system for immersive media. His title of talk is Scene Adaptive Imaging Technology for Content Production in Immersive Media. So, Mr. Tomioka, please start your talk.
Thank you for the introduction. Can you hear me? Okay.
Yes, okay.
Can you my slides? Okay.
Yes.
Okay.
Yes, okay.
Okay.
Everything is okay.
Okay, thank you. I'm Kohei Tomioka from NHK. It is an honor to be presenting here. Today, I'm excited to introduce our new proposal, a Scene Adaptive Imaging Technology. Okay, cool. Let's begin with an overview of my presentation. I'll start with the introduction, providing some background on our research, and then I'll present the overview of the Scene Adaptive Imaging technology we propose. And next, I'll dive into the key technology, the area control image sensor. And subsequently, I'll showcase the result of experiments that demonstrate the image quality improvements achieved with Scene Adaptive Imaging technology. Finally, I'll conclude with a summary. Now let's begin with the introduction. So NHK has been dedicated to developing the advanced 8K video systems. Our work on 8K started back in 2000, and in 2018, we successfully launched 8K satellite broadcasting. During the Tokyo Olympic in 2021, we achieved 8K broadcasting as well. Currently, our research is focused on immersive media for the 2030 to 2040 media environment, which includes 360 degrees videos, AR, VR contents, 3D images, and more, providing a high immersive visual experience. One of the challenges in imaging for immersive media is the need for high-speed readout and signal processing beyond 8K. In this slide, we are comparing video system parameters. For 300 degrees video, our 30K by 15K imaging system is recommended according to ITR standards. And this high resolution system results in a pixel rate of up to 56 gigapixel per second, which is more than 10 times higher than 8K. And to achieve the immersive visual experiments we aim for, it is crucial to have a video system capable of handling such very high pixel rate. Another challenge in imaging for immersive media is the task of integrating high resolution, frame rate, and dynamic range. In 360 degrees imaging, diverse subjects with varying movement and brightness coexist within the same frame. To accurately capture these subjects, a system with high resolution, high frame rate, and high dynamic range is necessary. However, these parameters are in a trade-off relationship, making it extremely challenging to develop an image sensor that meets all required performance. To tackle these challenges, we propose Scene Adaptive Imaging technology. In our proposed Scene Adaptive Imaging technology, we enhance image quality by locally control imaging parameters based on characteristics of subject in each captured area. For example, areas with fine details are captured at standard resolution and frame rate. At the same time, fast-moving subjects are captured at 1/4 resolution and 4 times the frame rate. Additionally, we utilize the bright mode for capturing bright areas, reducing exposure time to 1/4, and low light mode for dark areas, lowering the frame rate and increase exposure time by 2 times. By adjusting imaging parameters according to the subject, we overcome the trade-off relationship of imaging parameters and improve image quality and achieve the desired performance. The key technologies behind Scene Adaptive Imaging are the area control image sensor and scene information analysis. The area control image sensor is a sensor that can locally adjust resolution, frame rate, and exposure time for each area. It receives area control signal from scene information analysis, as shown in this diagram. Scene information analysis is a technology that analyzes the sensor's output and automatically determines the best imaging mode for each area. This feedback control allows the sensor to capture images in the optimal mode according to the subject characteristic. So to achieve scene adaptive imaging technology, we fabricated a 1K by 1K resolution test chip for area control image sensor. This chip divides the pixel array into a 16 by 17 grid of control blocks. And different operational modes can be assigned to each control block based on an externally input area control signal. There are 4 supported modes. Normal mode captures images at 64 by 64 resolution per control blocks, and frame rate is 60 FPS. And the fast mode allows for 1/4 resolution of the normal mode, and it's 32 by 32 pixels with a 240 FPS frame rate. Bright mode maintains the same resolution and frame rate as normal mode, but enable a 1/214 exposure time using an electronic shutter. And low light mode reduce the frame rate to 30 FPS to double the exposure time. This sensor achieves various variation modes by adding switches to the conventional pixel structure. This figure shows the pixel architecture of the area control image sensor. The pixel array is divided into 16 by 17 grid of control blocks, each containing 64 by 64 pixels. And labeled as ABCD in this diagram, this sensor has a structure consisting of 4 pixels in a unit. And each pixel shares its output with 4 neighboring pixels. We added extra switches here to control the charge transfer of photodiodes in each pixel. These added switches are individually controlled by the control signal from the mode controller. By controlling the switches operation, we can select which pixel from ABCD to read, as well as just exposure time and the pixel binning. With this pixel structure, different resolution, frame rate, and exposure time can be set for each control box. In this diagram, I will provide a detailed explanation of the pixel readout control method. By using additional switches, we enable 2 pixel signal readout method. The first method is sub-pixel readout, where we input the readout pulse to only one selected pixel among ABCD. This allows us to read out each ABCD pixel one by one in sequence with 4 readout scans. Therefore, sub-pixel readout separates ABCD pixels into 4 frames, providing a highly resolution output. However, it requires 4 scans, which makes the readout process relatively slow. The second method is pixel binning readout, where the switches input the readout pulse to all ABCD pixels every time. As a result, the output of ABCD pixel is combined into aggregated signal. Though it decreases resolution, but it achieves 4 times faster readout speed. Controlling the switches allow us to prioritize either resolution or frame rate during the readout process. So, and this slide demonstrates how the 4 operational modes are switched using different readout method. The horizontal axis represents time, and the slanted line indicates the pixel signal readout scans. Vertically, there are 16 control blocks arranged, and we scan from block 1 to block 16 sequentially. The scan interval is 1/240 seconds. By switching between the 2 readout methods, as explained earlier, we can switch between 4 operational modes as shown in this diagram. A represents the normal mode, where we use sub-pixel readout to read out ABCD pixels individually in 4 scans, resulting in a frame rate of 60 FPS and exposure time of 160 seconds. And B, first mode, utilizes a pixel binning readout, which aggregates ABCD pixels, reducing the resolution, but achieving a readout speed of 240 FPS. And C, a bright mode, is similar to a normal mode, but with the electronic shutter function enabled, limiting the exposure time to 1/240 seconds. And D, low light mode, involves alternating subframe readout and 4 frame readout poses, allowing us to set the exposure time for each pixel to 130 seconds, effectively doubling the exposure time. By controlling the readout method during the 1/240 seconds scanning period, we can achieve various resolution, frame rate, and exposure time for readout at the same frame. So next, I will share the results of imaging experiments conducted with the area control image sensor and enhancement in image quality achieved. These are captured videos using the prototype area control image sensor. In this comparison, we have 2 sets of videos. The left side is captured using the conventional method, where all frames have the same imaging parameters. The right side is captured using the proposed method, where imaging parameters are controlled locally. For example, rotating subject captured in fast mode, dark subjects in low light mode, and bright subjects in bright mode. Here we compare images captured using the proposed method and the conventional method. The proposed method has demonstrated improvement in motion blur and overexposure and underexposure. For example, in the region capturing a rotating object, motion blur was improved here. And in areas capturing bright subject, overexposure was improved, and in areas capturing dark subject, underexposure was addressed. This improvement clearly indicates that the area control of imaging parameters enables the enhancement in image quality. And next, we conducted an experiment to verify the function of scene information analysis. For this purpose, we developed a scene adaptive imaging system with real-time feedback based on brightness distribution analysis. Here is an overview diagram of the system. We integrated the functionality of analyzing the brightness distribution analysis on FPGA board. The determination result is promptly sent back as a feedback signal to the area control image sensor. The analysis and feedback control are completed within a single frame period. Therefore, the system enabled automatic capture in the optimal mode for each blocks, depending on the subject brightness distribution. And this slide shows the captured video images and feedback signals obtained by the proposed system. On the left side, we have the captured video, and the right side, we have the corresponding feedback signal. Based on the brightness distribution, the system automatically assigns 3 different modes: low light, normal, and bright. Here is a comparison in still images. The area with low light mode applied tracks the moving hand, while the region illuminated by the LED light switches to bright mode. Furthermore, the area with intermediate brightness switches to normal mode. So these results showcase the system's capability to apply feedback control to the operational modes based on brightness distribution analysis. Okay, finally, I will conclude with a summary. So during this presentation, we introduced a scene adaptive imaging system that locally controls imaging parameters based on a scene characteristic for immersive media. And through prototyping, we successfully improved the image quality of captured videos by applying area-based control imaging conditions. As our next step, we will work on reducing the control block size of the area control image sensor and developing a scene adaptive imaging system with practical resolution. Thank you for your kind attention. Thank you.
Okay, thank you, Mr. Tomioka. And then now, is there any question from the audience?
I don't have any question, but I just wanted to thank Dr. Tomioka for his very interesting, eye-opening presentation. I didn't know how advanced the imaging technology is nowadays. And I assume the technology that he presented has a huge impact on compression of immersive video or imagery in the new imaging systems. I assume it was very interesting talk where he just developed different blocks where he could improve the quality of the overall image. So maybe I can ask him what could be the potential impact of this technology on compression of the images, which I assume should be a big challenge nowadays.
Yeah.
With a lot of bandwidth issue, you know, if you reduce the size of the video and or images, it can significantly impact the communication of imagery scenes.
Thank you for your comment. And this technology has, I think it is useful not only for immersive media, but we can use this technology for various applications. Thank you for your comment.
Thank you.
Okay, any other questions? Okay. Oh, okay. Now I think it's. Is it okay to close the?
Yeah. So I just wanted to thank you all for participating into this session. Wanted to apologize for the hiccup that happened beginning of the session. We had to share a new meeting link with everyone. Yeah. Once again, I want to thank you from our guest speakers, Dr. Tomioka and Dr. Mehrabi for their interesting talks. Thanks to Hiroshi for organizing a very interesting talk on behalf of his technical committee. I would like to encourage everyone to follow up the announcement that we sent through the email address of the technical committees, and stay tuned with the presentation that we are going to offer to you in the next coming months. Thank you again. Hope you have a good day. and hopefully we'll meet again sometime soon in the coming months. Thank you. Thank you.
Thank you very much.
Thank you,
Thank you
everyone.
very much.
Take care. Bye-bye. Bye-bye.
Thank you. Bye.